Our team, Arti Chauhan, Thomas Weldon, Satish Gupta, and I myself, Dhruv Patel, worked on the project of sepsis prediction. The motivation for choosing this project and the topic regarding sepsis is because it is the leading cause of decomposition and mortality in US hospitals. Approximately 1.7 million adults develop sepsis, resulting into 270,000 deaths. We propose to add a clinical prediction benchmark task using the data from MIMIC 3 to predict in real time the onset of sepsis. It has been reported that sepsis is frequently underdiagnosed in the hospitals despite being mentioned in the discharge notes. Our goal is to predict sepsis shock 6 hours before occurrence. Data source and pre-processing. We divided this into 3 steps. So the data source being used is PhysioNet Mimic 3 dataset. The first step was to detect sepsis criteria and cohort construction. For this, we have to identify the case and control patient. The case and control patient are being identified using the SOFA score greater than 2. The next step is to define the observation and prediction window. We define our observation window to be 12 hours and prediction window to be 6 hours. The next step will be feature engineering. Our research shows that vitals and age have high predictive power for this task and hence were chosen as a base feature set. Then we go to the data pre-processing step, for example, filling out missing data or handling data using Wisconsin technique. And then after the pre-processing of the data, it goes to the modeling, where we used support vector machine, great XGBoost, multilayer perceptron, logistic regression, and LSTM models. Here is a quick snapshot of exploratory data analysis. We see that the patient's age distribution is slightly skewed towards right. See that on the right, the distribution of ICU length of stay is slightly skewed left. The infection type, the two main infection, cardiovascular infection and respiratory infection, comprises 50%. Length of stay for patient with suspected infection was about 0 to 4 days. Let's talk about the results, baseline models, balanced data set. We used vitals data, vitals plus GCS, vitals plus lab, and we comprised all of them together. As you can see, all the scores, accuracy, F1 score, recall, and precision, was increasing when we added GCS and lab with vitals. And when we comprised all of them together, the score has been improved dramatically. Gradient boosting works well compared to support vector machine, logistic regression, or multilayer perceptron. If we further dig down, the important feature extracted using random forest classifier were GCS verbal mean, albumin mean, and lactate PTP were the main features extracted. Here are the confusion matrix for all the algorithms that have been used. Gradient boosting, SVC, logistic regression, and multilayer perceptron. Out of all, gradient boosting works to be well. The type 2 error to be as low as possible. And we can see that in gradient boosting is the lowest compared to all. In gradient boosting is 0.04. SVC, it's much higher than gradient boosting. Logistic regression is quite near to the gradient boosting, but still a little bit higher. And multilayer perceptron is double of the gradient boosting. Here are the baseline models for the imbalanced dataset. We can see here that the recall for gradient boosting in the imbalanced dataset is 80%. Since gradient boosting worked well in the balanced dataset, it gives type 2 error, which is slightly higher than was in the balanced dataset. We've also tried to perform a LSTM model. And surprisingly, the recall is higher, but it's not doing well compared to the gradient boosting algorithm. As you can see, it does well with the training data set, but with the testing data set, it is giving the high variance. The key takeaway from this study is this study presents a machine learning based approach to predict sepsis onset time using commonly available features such as vital, GCS, and lab results for ICU patients, relying on ICD code. The study clearly quantifies predictive power of each feature set. This helps with interpretability of models as clinicians can gauge which feature is adding most value and hence can reason about it using their domain knowledge. The study also evaluates the robustness of model in presence of imbalanced dataset, which is common in real-world setting. The challenges faced in the study was sepsis detection criteria. It was very hard to separate the case and control patient. Finally, we went out with research and said we're going to use SOFA score greater than equal to 2 to identify. The setting up the PySpark environment was challenging in terms of setting up the environment variable in the local machine. In the imbalanced dataset, we saw that the number of case patients had a sepsis shock was much lower than the control patient. So that was the biggest challenge on what data to use for our models. Selecting the control patient from the pool of many control patients was also a problem, and we wanted to pick the best control patient for the balanced dataset. Text feature extraction, it was a challenging problem because the clinical notes and EHR were very hard to interpret and use it into our model. Our RNN LSTM model technically was supposed to work well, but didn't work well for some reason. The future work, use NLP to extract the features from the clinical notes. We can use different ensemble methods. We can use modern deep learning healthcare algorithms that are developed by experts today. We can consult to physicians and clinical scientists to get better understanding of sepsis prediction. We can also develop on pre-trained model by experts. Here are the references that we use the information to get our results and understanding of sepsis prediction. We would like to acknowledge Professor Jiming Sun. We would like to acknowledge our teaching assistant, Mr. Bin, who was very helpful and responsive in our research. Thank you.